Good morning, students. Welcome back to Sunain Sir's online classes. In this video, I am going to explain you Refraction at Curved Surfaces chapter part 4, which contains all miscellaneous questions. First, let us see how do you verify focal length of lens depends on surrounding medium. So, in this question, what he is asking is he wants us to verify that focal length of lens depends on surrounding medium. It means when we keep lens in air, when we place lens in air, its focal length will be one value, whereas if we place lens in water, then its focal length changes. It means its focal length increases. So it means that focal length of the lens is not at all constant. It will change as per the surrounding medium. So we need to verify this with an activity. So first what we need to do is we need to take a glass beaker and place a stone at the bottom of it. Take a glass beaker and place a stone at the bottom of it. So before going to this activity, I would like to say that I would like to recall your basics that virtual image of virtual image will always form when object is placed between focus and optic center. So whenever object is placed between focus and optic center, only then convex lens will form virtual image. Otherwise lens will not form virtual image. That is, when you place object beyond focal length, when you place object, for example here, beyond focal length, then real image will form. In this way real image will form, whereas in order to form virtual image, so the limit is object should be placed up to focal length only. If you place object beyond focal length, then it will form real image. It means real image we cannot see directly with our eye. In order to see real image, we need to place screen. So in this activity there is no chance to place screen. That is why we can see only virtual image in this activity. It means we can see image of the stone which is placed at the bottom of the beaker in the lens. If we see the image of the lens in the image of the object in the lens, then that is called virtual image. So in this activity we have chance to observe only virtual image. That is why, so virtual image means, here you can see in this picture, you can see this is a convex lens. In this convex lens, inside this lens we can see the image of steps and a statue. So similarly, this is a convex mirror. In this convex mirror we are seeing image of car and parking area of the house. Similarly, in this convex mirror we can see image of a house. In this way, the image whichever we see inside the lens or inside the mirror is called virtual image. And in this activity we are going to observe virtual image, not real image. So in order to observe virtual image, so limit is object should be placed up to focal length. Beyond focal length, if you place object, then it will form real image. Behind the focal length, it means inside the focal length or inside the focal point, if you place the object, then you can observe a virtual image. So in this activity, remember that in this activity, in order to see the image of a stone which is placed at the bottom of the beaker, then in order to see the image of the stone which is placed at the bottom of the beaker with the help of convex lens, we need to see this. In order to see this, we need to place this lens until its focal length. If you lift it beyond focal length, then you cannot see the image of the stone. Now let us come back to the activity. Till now whatever I explained is something relevant to this, but it is not actual activity. So actual activity is, first what we need to take, what we need to do, we need to take a glass beaker and place a stone at the bottom of it. Now using a convex lens, try to see the image of the stone in the lens by keeping it exactly above the stone. So what you need to do is, take a glass beaker and at the bottom of the beaker place a stone. Now take a convex lens. With the help of a lens holder, try to see the image of this stone inside the lens. It means try to observe its virtual image and slowly lift this slowly lift this convex lens till where you can see its image. It means till here, if you can see the virtual image, then mark this height. Beyond this you cannot see the virtual image, then mark this height. Okay, to observe the virtual image, we need to place the object till the distance equal to or less than focal length. It means to observe the virtual image of this stone inside the lens, we need to place this lens till this focal length value. Beyond the focal length value we cannot see virtual image, because virtual image will not form, real image will form, but here there is no possibility to place a screen. That is why you can see the image of the stone until this point, then mark this point, mark this height and measure this height. That will give you focal length of the lens. Now mark the height on the vessel until where image of the stone is visible in the lens. For example, if that height is 20 centimeters, then this distance is equal to focal length. This 20 centimeters is equal to focal length. Now pour the water in the vessel and observe the same way. Now pour the water in the vessel and start observing the stone. After pouring water, start observing the stone by using convex lens. In this way, slowly lift the convex lens and mark the point until where you can see the image of the stone in the lens. That point, mark that height. Beyond that height you cannot see the virtual image of the stone, because till one point only, it means till focal length only, lens will form virtual image. Beyond focal length, lens will not form virtual image. Now mark the height on the vessel until where image of the stone is visible in the lens. So in this way pour water in the beaker and try to observe the image of the stone inside the lens and slowly lift the lens till where you can see its image. Beyond that point you cannot see its image. It means this point is equal to focal length. So previously without water, if this is the height where you can see the image, now after pouring water this height increases. This will be the height till where you can see the image. It means previously if this height is 20 centimeters when there is no water, when there is air, now this height will be around 30 centimeters when you pour water. It means this height will give you focal length. This height is nothing but focal length, because till focal length only you can see the virtual image. Beyond focal length it will not form, convex lens will not form virtual image, it will form real image. That is why when there is air, focal length is 20 centimeters, but when there is water, focal length will be 30 centimeters. From this we can verify that focal length of convex lens always depends on surrounding medium. It means it will increase in water. In this case height will be more than 20 centimeters, it will be around 30 centimeters. This distance is equal to focal length. It means focal length of lens has increased when water is poured. From this we can conclude that focal length of lens depends on surrounding medium. It will depends on surrounding medium. Now let us see another question, that is concave lens. How concave lens behaves as diverging lens. Concave lens is also called as diverging lens, and this is diagram is important regarding 2 marks. See, this is concave lens, and when light rays traveling parallel to principal axis incident on concave lens, they will diverge from each other. They will go away from the lens. They will diverge from each other, and in this side there is no chance of these rays meeting each other. That is why when you extend these light rays backwards, all these light rays will meet at this point. This point is nothing but focal point or focus. So this is important regarding 2 marks. How light rays will diverge when they are incident on concave lens. So they will diverge away from each other, and when you extend them backwards, they will meet at focus. Now let us see one case of image formation in case of concave lens. Image formation when object is placed between focus and center of curvature. This is object when it is placed between focus and center of curvature. Now let us take 2 light rays. One is light ray traveling parallel to principal axis. After incident on lens, it will go away from the lens in this way, and another light ray which is passing through the optic center, it will go straight without any refraction, without any deviation. Now this side there is no chance for these 2 light rays to meet each other. That is why when you extend them backwards, these 2 light rays meet at this point where image forms, where image formation takes place. This is the image. In this case, since image is forming on the same side of the object, this is it is virtual image, and it is here you can see it is a diminished image, and this is erect image. Since all virtual images are erect, it is a erect image, and it is formed between focus and optic center. It is formed between focus and optic center. This is also important regarding 2 marks. Let us see image characteristics. Image formed is virtual, and it is a diminished image. It is a erect image, and it is formed between focus and optic center. Let us see one more question, that is explain different terms in lens. First one is center of curvature. Center of curvature is nothing but center of sphere which curved surface is a part. For example, if this is a curved surface of a lens, if you take this as a lens and this is one of the curved surface of the lens, now if you complete this curved surface, it will form a sphere. Center of the sphere is nothing but center of curvature. So center of curvature is nothing but center of the sphere of which curved surface is a part. Principal axis is the line that joins center of curvature and pole, or center of curvature and optic center. And optic center is nothing but midpoint or center point of the lens. Midpoint or center point of the lens is called optic center. Radius of curvature is nothing but distance between optic center and center of curvature is radius of curvature, and radius of curvature is always equal to r is equal to 2f. Next one is focus, the point where light rays moving parallel to principal axis meets. The point where light rays moving parallel to principal axis meets. Focal length is the distance between optic center and focus, and pole is nothing but, if you take lens means it will consist of two curved surfaces. Center point of this lens is called optic center, whereas if you take one curved surface, this midpoint or center point of this curved surface is called as pole. Pole is similar to optic center. For two curved surfaces we will define as optic center, for one curved surface we will define it as pole. Now let us see different types of lens. This is double convex lens, you already know. This is double concave lens, you already know. And if one of the surface is plane, then it is called plano-convex lens and plano-concave lens. And this is concavo-convex lens, and this is convexo-concave lens. Next one is, can a convex lens behave like diverging lens? We know that convex lens is a converging lens. It will converge all the light rays passing through it. It is a converging lens. In this way it will converge all the light rays. Now in the question he is asking that, can a convex lens behave like diverging lens? It means, can a convex lens behave like convex lens? So answer is yes, it can behave like diverging lens when it is placed in a medium whose refractive index is greater than that of lens. For example, so how can we decide that a lens is converging or diverging? We will decide it based on focal length. If focal length is positive, then it is a converging lens, and if focal length is negative, then we will consider it as diverging lens. Now in order to find focal length, we have one formula, that is 1 by f is equal to n2 by n2 by n1 minus 1 into 1 by r1 plus 1 by r2. So this is the formula for convex lens, and in this formula this term 1 by r1 plus 1 by r2 is always positive. Now if you take this term can be positive or negative. n2 by n1 minus 1, it can be positive or negative. Now if you take n2 by n1 minus 1, if you consider this term, if you consider n2 by n1 minus 1, this n2 by n1 minus 1 will be positive when n2 by n1 greater than 1. It means if n2 is greater than n1, then n2 by n1 minus 1 will be positive. Whereas if n2 by n1 is, if n2 by n1 is less than 1, it means if n2 is less than n1, then this whole term will be less than 1 and this whole term will become negative. If n2 by n1 is less than 1, then focal length will become negative. It means if refractive index of the medium is greater than refractive index of the lens, it means if lens is made up of water, for example, if lens is made up of water, refractive index of the lens is n2 is equal to 1.33. Now this lens, if it is placed in glass, it means n1 is equal to 1.5. Now if you take focal length, 1 by f is equal to n2 by n1 1 by 1.33 by 1.5 minus 1 into 1 by r1 plus 1 by r2, say this as constant. Now 1.33 by 1.5 is equal to around 0.7 minus 1. So this is 0.7 minus 1 is minus 0.3. So focal length is changing into negative. So in this case, this convex lens will behave like diverging lens. It means when lens is made up of refractive index and some refractive index, and it is placed in one medium whose refractive index is greater than the refractive index of the lens, then it will behave like diverging lens. So similarly, an air bubble is placed in water will have a shape of convex lens. An air bubble, we know that inside the water there will be air bubbles. In some cases air bubbles will form, and these air bubbles will have the shape of convex lens, but they will behave like biconcave lens, because the reason is refractive index of this lens is n2 is equal to 1, whereas refractive index of surrounding medium water is n1 is equal to 1.33. because refractive index of surrounding medium is greater than refractive index of the lens, it will behave like diverging lens, concave lens, though it is having the shape of convex lens. Next, can a virtual image be photographed? Yes, we can take a photograph of virtual image. Similarly, we can take a photograph of mirage also, because mirage is also a virtual image. Example is here, daily we will see image of ourselves before going to work inside the mirror, and similarly we can take a photograph of our image inside the mirror. This image which is inside the mirror, here in the picture you can see a person is taking photograph of his own image inside the mirror. Inside the mirror, the image which is forming is nothing but virtual image, and this person is taking virtual image. He is capturing a photograph of virtual image. So this is the proof for virtual images can be photographed. Next, suppose you are inside the swimming pool and your friend standing outside. Now, do you find your friend taller or shorter? Answer is, you will find your friend taller than actual height, because light rays bend away from the normal when they enter air from water. When light ray is traveling into air from water, light ray will bend away from the normal. Because of this reason, you will find your friend taller than actual height. Similarly, for a fish inside water, you will appear taller than your actual height. Next, focal length of system of lens. For example, if I have two lenses which are placed side by side in this way, now if I want to find net focal length of these two lenses which are separated by a distance d, then net focal length is given by 1 by f net is equal to 1 by f1 plus 1 by f2 minus d by f1 f2 minus d by f1 f2. So this is the net focal length of system of lens. If distance between the lens is 0, it means if they are attached to each other, then 1 by f net is equal to net focal length is equal to 1 by f net is equal to 1 by f1 plus 1 by f2 minus d by f1 f2, but distance between them is 0, that is why it is minus 0. So finally net focal length will be equal to 1 by f net is equal to 1 by f1 plus 1 by f2. Next, what is the focal length of double concave lens which is kept in air, whose r1 is equal to 30 centimeters, r2 is equal to 60 centimeters, and refractive index n is equal to 1.5. Now we need to find focal length. So focal length is given by, in the question he is asking to find focal length of concave lens. So for concave lens, in order to find focal length, we have formula n2 by n1 minus 1, n2 by n1 minus 1 into 1 by r1 plus 1 by r2 with a minus sign in front of the formula. So 1 by f is equal to minus of n2 is 1.5, n1 is, it is kept in air, that is why it is 1, minus 1 into 1 by 30 plus 1 by 60. So this is minus 0.5 into 1 by 30 plus 1 by 60, LCM is 60, and this is 320. So this is 1 by f is equal to minus 0.5 into 1 by 20. So 1 by f is equal to minus 0.5, I can write it as 1 by 2 into 1 by 20. So this is minus 1 by 40. 1 by f is equal to minus 1 by 40, whereas f is equal to minus 40. So focal length of the concave lens is minus 40. Next question. A convex lens has equal radii of curvature r and n is equal to 1.5. Find focal length. So a convex lens is having equal radii of curvature, r1 is equal to r2 is equal to r, and n is equal to 1.5. So we need to find focal length. So 1 by f is equal to, formula for convex lens is n2 by n1 minus 1, that is 1.5 minus 1 into 1 by r plus 1 by r. 0.5 into 1 by r plus 1 by r is 2 by r. So this is 0.5 into 2 is 1 by r. So 1 by f is equal to 1 by r, f is equal to r. Next question. Find focal length of plano-convex lens whose radius of curvature is r and refractive index is n. So we need to find focal length of plano-convex lens. Plano-convex lens means one surface will be plane. So for plane surface always radius will be infinite. R1 is equal to infinity. Second surface radius of curvature is given as R2 is equal to R, and refractive index is given as n. Now, so we need to apply focal length lens maker's formula for convex lens. So it is n2 by n1 minus 1, n2 is focal length of the lens is given as n, by n1 it is kept in air, that is why n1 is 1, minus 1 into 1 by r1 is 1 by infinity plus r2 is r. So this is n minus 1 into 1 by infinity is 0 plus 1 by r. So 1 by f is equal to 1 by f is equal to 1 by f is equal to n minus 1 into 0 plus 1 by r is 1 by r. So 1 by f is equal to n minus 1 by r, whereas f is equal to r by n minus 1. This is also very important problem regarding 4 marks. Regarding 4 marks, this is very important problem. F is equal to r by n minus 1 for plano-convex lens. Next one, let us see one multiple choice question, that is, which is true? Image distance for virtual image is greater than object distance in case of convex lens. So in case of convex lens, when virtual image is formed, so when virtual image forms in case of convex lens, when object is placed between focus and optic center. So here, for example, if we place object, then virtual image forms at this point. It means this is object distance and this is image distance. So in this case, image distance is always greater than object distance. V is greater than U. So image distance for virtual image is greater than object distance. So this is true. Image distance for virtual image is not greater than object distance. This is false. Convex lens always forms real images. This is false because convex lens will also form virtual images also. Convex lens will form both real images and virtual images. This is also false. It always forms virtual images. This is also false because convex lens will form both real and virtual images, whereas concave lens will always form virtual images only. So in all the four options, first option is true. Next, which is not used to make lens? Water, glass, plastic, clay. So in all the three, if we observe in all the four, water is transparent, glass is transparent, plastic also transparent. We can also have plastic materials, transparent plastic materials, whereas clay is not transparent. That is why we cannot make lens with clay, because lens should be always made with transparent material in order to form images. So we cannot use clay to make lens. I hope this is clear. If you have any doubt, you can message me or you can contact me at any time. Thank you for watching the video.